Welcome to part 3 of two-stage opamp circuit analysis. So this is the two-stage opamp with Miller compensation technique. So this is the compensating capacitor. In the previous video we saw the small signal diagram of this circuit. We are again seeing the same thing now. So this is the circuit diagram, the AC small signal analysis. So with CC as the compensating capacitor between the output and input of the second stage, and using KCL at node A and node B, we wrote the expression for V naught dash in terms of V in and V naught given by this expression, and similarly at node B we could able to get the expression for V naught in terms of V naught dash. We actually uh, wrote the SFG for that small signal two-stage operational amplifier with V naught dash and V naught as the variables, and using equation 1 and 2 what we obtained using the current at nodes A and B, we could able to write the small signal SFG for that small signal model using equation 1 and 2, which we discussed in the previous video. And this is the transfer function for this signal flow graph, considering this, that is minus gm1 divided by g1 plus s into c1 plus cc multiplied by this quantity as a forward path gain divided by 1 minus the loop gain. So why it is minus is because we have a positive feedback. So since both are plus, it is 1 minus L1, and since we have only one loop and only one forward path, so we have P1 1 minus L1. So delta 1 is also 1. So delta 1 is nothing but the poles, the loops which are not touching the first forward path. So that is equal to actually 1. Delta 1 is equal to 1. So we are actually rearranging the terms. Here we are taking minus gm2 outside, and we can write it as uh, so now this will be written as 1 minus, so that's what we are writing here. So it is 1 minus SCC divided by gm2, and we are naming this. So we have taken the LCM here, since the denominator over here and here are same, so they are going to cancel out, and this entire term is going to be coming in place of 1 here. So that's what we have here, and you can see the minus sign is here, and then we are multiplying this into this. That's what we have done here, and we have taken out g1 g2 as common factor in the denominator. So we have taken this as common factor, and the first term happens to be 1, plus now we have g2 here, so g1 is left out, g1 is here, so 1 over g2 is left out. We don't have anything here, so g1 g2 both are left in the denominator, and of course for this we don't have neither g1 g2, that's why in the denominator we have g1 g2, and here also we don't have any term here. When I take out g1 g2, now I'm going to end up with g1 g2 in the denominator. So by doing these simple mathematical steps, so we are now rewriting, so 1 over g1 and 1 over g2 which were taken as a common factor. So I will write this as R1 and R2, the R of first stage and the R of second stage, multiplied by GM of first stage and GM of second stage. So as we can see now, this is GM into R1, GM1 into R1 of the first stage, GM2 into R2 of the second stage. This happens to be the gain of first and second stages. And of course, we have in the denominator we have taken out S common and S square common. Now this is the terms we are left out in the denominator. Now we know that denominator, the poles which were there at P1 dash and P2 dash without compensation have been moved to P1 and P2. Now the corresponding frequency of P1 is omega P1, the corresponding frequency of P2 is omega P2. So since we have only two poles in the compensated circuit also, since the number of poles will not change, so now we can see the denominator of V naught by V in will going to have the poles at omega P1 and omega P2. So this is what is the denominator will look like for this overall transfer function. So let us see only the denominator of V naught by V in. So denominator of V naught by V in can be written as just multiplying these two terms here. So as we saw here, So we are simply multiplying this term and this term. We end up with these four terms here. So out of these four terms, so let me just take out S as common factor in these two. I'll end up with 1 over omega p1 plus 1 over omega p2, and of course we have S squared divided by omega p1 into omega p2. As you can see now, the coefficient of S is omega p1 plus omega p2. So this omega p1, omega p2 are the pole frequencies corresponding to the pole location after compensation. We know that after compensation, P1 dash is moving closer to the imagined axis and P2 dash is moving away. So this clearly shows that this omega P1, the corresponding frequency of this P1 is very small compared to omega P2. You can see omega P2 is moving far away. This omega P1 is going closer to 0. Now since omega P1 is very small compared to omega P2, over here, so this is omega P1, 1 over omega P1, this is 1 over omega P2. So since omega p1 is very small and omega p2 is very large, so the one which has got a lesser value in the denominator has got more dominant role than the value of frequency which is larger. So that's why out of omega p1, 1 over omega p1 and 1 over omega p2, we are not considering 1 over omega p1 because the value contributed by 1 over omega p2 is very small compared to 1 over omega p1. So we are retaining only 1 over omega p1 as the coefficient of S. Now let us have a look at the denominator of equation 3. So let us again look into this is equation 3 where we had taken out S common factor and S square common factor. Now these are the terms which are the coefficients of S, and these are the terms which are the coefficients of S square. So let us go back and try to see the same thing now. So this is the denominator of that equation 3. Now we know that the denominator of the expected equation can be equated to the denominator of the actual equation. Now you can see the coefficient of S will going to have terms 1 over omega p1 plus 1 over omega p2, and which can be approximated to only 1 over omega p1 because the contribution of 1 over omega p2 is very small compared to 1 over omega p1. So we have 1, 2, 3 terms which are the coefficients of S. So now this should be equated to 1 over omega p1, and the coefficient of S square will be 1 over omega p1 and 1 over omega p2. Now since if the value of coupling or compensation capacitor Cc is far greater than C1, and if C2 is far more than C1, so under this condition, usually the compensation capacitor is more compared to C1 and C2 is always more than C1. So with these conditions, as you can see now, this is C1 CC and here it is C2 and CC, and we have this R1 GM2 R2 CC. So we have 1, 2, 3 terms. Out of these three terms, this Cc is multiplied by Gm2 R2 as well as R1. So this term happens to be the large contributor among all the coefficients of S. So we retain only this term. We neglect R1 into C1 plus Cc plus R2 into C2 by C2 plus Cc. So this is the term which is contributing more to the coefficient of S rather than these two. So we neglect these two terms compared to this. So that's why we are writing the denominator of the expression as S into R1 GM2 R2 into CC. Of course, since we know that CC is far greater than C1 and the C2 is far greater than C1, so among the coefficients of S square, we retain this C2 and CC as the main contributors because the other two terms, that is C1 into C2 and CC into C1, are contributing less because CC is more than C1 and C2 is more than C2. Naturally, the contribution by C2 CC is more compared to these two terms. So that's why we are retaining only C2 into Cc. Of course, it is multiplied by R1 and R2. So we end up with the denominator of the expression as 1 plus S into R1 Gm2 R2 Cc plus S square into C2 Cc R1 into R2. So equating this equation that is 1 plus S by omega P1 plus S square by omega P1 into omega P2. So this is not equation 4. So we need to equate this equation, that is, we'll name it as 4 dash. Equation 4 dash and 4 we'll want to get omega P dash. So now this is actually 1 over omega P dash. So we can write this is omega P1. Omega P1 can be written as 1 over R1 R2 Gm2 into Cc. Now we know that the quotient of A square here is 1 over omega P1 into omega P2. So now omega P1 into omega P2 can be written as 1 over C2 Cc R1 R2. By knowing the value of omega P1 and substituting it here, so omega P2 becomes Gm2 divided by Cc. So this is the expression for omega P1 can be obtained from this quotient of S, equating this denominator and this denominator. We know that omega P1 can be represented by this, and the quotient of S square is actually 1 over omega P1 into 1 over omega P2. So that can be using this omega P1 omega P2 is equal to 1 over C2 Cc R1 R2, and replacing omega P1 by this, so we'll get the expression for omega P2 as Gm2 divided by C2. Now this way we're going to have this P1 dash move to P1 and P2 dash will be moved to P2 now. This is the location of the 0, which is onto the right hand side. Its location is actually Gm2 divided by Cc. The location of 0 is at onto the right hand side, which is Gm2 divided by Cc. So this is what we are trying to find out. So the position of 0 is at omega z. This is omega P1. This is omega P2. This is the location. Now 0 is there onto the right hand side with its value as Gm2 by Cc, and the pole P1 has been moved to this position, and P2 is actually minus Gm2 by Cc2. This is C2 now. So earlier P1 dash was at minus of 1 over R1 C1. Now it has been moved. You can just have a look at earlier, whenever there was no compensation capacitance, the resistance was R1 and the output capacitance was C1. So once we put this compensation capacitor, because of the Miller capacitance, so this Cc along with the gain of this second stage, which is Cc into R0, Cc into R2 of this this stage will be added onto the existing capacitance C1 here. So when it is C1 plus Gm2 R2 into Cc, now that Gm2 R2 into Cc will be far greater than C1. So that's why it's actually this R1 into C1 will be replaced by, now this C1 is now replaced by Cc into Gm2 R2. So the pole position P1 dash, which is R1 C1, now you can see this C1 is now replaced by Cc times Cc into Gm2 into R2. Now this R1 remains the same. It is R1 into, instead of C1 it is Cc into the gain of the second stage. Similarly, the P2, which was due to 1 over R2 C2, now you can see C2 still remains the same. So instead of R2 it is 1 over Gm2. Because we are providing the negative feedback is going to reduce the resistance of the output stage. Now this way the P1, P2 will go into the earlier poles which were there at P1 dash and P2 dash will be moved to P1 and